And in the last video, we discussed about the introduction part of our nanomaterials and its characterization techniques. Today, in this session, we are going to discuss about the various microscopical analysis. So here, before going to our syllabus, we are very familiar with the microscopes. As I told, we are going to discuss about our microscopy. So let's see what do you mean by microscope. Microscope is a tool which can help you to see a tiny objects, either might be a living organism or non-living organism, which is having a size less than millimeter or micrometer, which is having a size of micrometers or in a millimeter, which we cannot able to see or distinguish through our naked eye. Such materials or such components or such things we are or objects we can see only through the microscopes. For example, in our high schools or in our 11th and 12th classes, we had done with the dissections like plant leaves, or we have a dissection of cockroach when we were in 12th. If you are from a PCB, means biological background, you might have very familiar with this dissection process. So there we were using these microscopes. So based on these principles, we have developed many microscopes in our engineering field to analyze the material properties or material distributions, or if there is a presence of voids. To analyze the various aspects of materials, we were developed different types of microscopes. Under that, first one we are discussing, that is known as optical microscopy. So optical microscopy is a type of microscope which uses visible light and a system which uses visible lights and a system of lenses to magnify images of a small sample. Image from an optical microscope can be captured by normal light sensitivity, like cameras to generate a micrograph. You can see here, you can see the human eye, where we can see the eye means human eye. So next to that we can see the eyepiece, where we are placing the projector lenses. Under eyepiece we are placing the projector lenses. Then we are placing the magnified real images. In between that we get the intermediate image, and next to that we have objective lenses, and after your objective lenses we used to place this specimen. Next to that we are having a condenser lenses and light sources. So this is how your optical microscopical structures will be. So here the function of this optical microscopy is to create a magnified image of a specimen. Consists of three basic functions of obtaining a clear, sharp image, changing a magnification and bringing to focus. So here the main principle of using this optical microscopy is to create a magnified image by combining an objective lens and making an inverted real image, and magnifies the image furthermore with an eyepiece to allow the user to observe it by a naked eye. So this is how we are using this optical microscopy. So where all we are using this optical microscopy, and in the study of microelectronics, in the study of nanophysics, biotechnological applications, and in medical diagnosis applications, we are using this optical microscopy. So what are the advantages of using this optical microscopy is, the cost is very minimum, and it looks like a simple device, and it's faster process, and can be operated by semi-skilled operator. It's not very difficult, it's not a difficult process to operate these machines. So if you have semi-skilled operator. That's enough to get the clear images by using optical microscopy. And it is easy to be integrated with the digital system for data storage and analysis. And as we have some advantages in every machines or every objects, we have some disadvantages. Like that, even we have some disadvantages in optical microscopy. That is, high level of magnification cannot be achieved by using optical microscopy. We won't get the high resolution of magnifications, and it's having it's having a low resolutions. It cannot able to analyze the pores which is present in the materials or which is present in the particular component or the specimen. And if there is a presence of voids or pores, etc., we cannot able to identify in a clear way or clear manner. So that are the some disadvantages we have. So to overcome from these, we are using a microscope known as scanning electron microscope. So scanning electron microscope produces images of a sample by scanning it with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contains information about sample surface, topography, and compositions. The principle of this scanning electron microscope is, or principle of operation is, an electron beam is focused onto the sample surface, kept in a vacuum by electromagnetic lenses. The beam is scanned over a surface of the sample. The scattered electron from the sample is then fed to the detector and then to the cathode ray tube through an amplifier where the images are formed, which gives the information on the surface of the sample. So here, let's see how the instrument will work. So first, the instrumentations or the instrument will having a heated filament as a source of electron beam, and we can see the condenser lenses, evacuated chamber, electron detector, amplifier, and CRT with the image forming electron. So this is how the arrangement will be. You can see in this slide, you can see in the top most of your slide, you can see the electron gun. Next to that, you can see the electron beam and first condenser lens you can see, then spray aperture, then second condenser lens you can see, X-ray detector, objective lenses you can see, and deflection coils, and final lens aperture you can see, black scatters you can see the samples, and vacuum pump, as well as secondary electron detector you can see. So as the electron beam traces over the sample, it interacts with the surface of the sample, dislodging secondary electrons from the surface of the specimen in unique patterns. A secondary electron detector attracts those scattered electrons, and depending on the number of electrons that reach the detector, registers different levels of brightness on a monitor. Additional sensors detect black scattered electrons, that is, electrons that reflect off the specimen surface, and X-rays, that is, emitted from the specimen surface. Dot by dot, you can see the dot by dot process in the red color. So dot by dot or row by row, an image of the original object is scanned onto a monitor for viewing. So scanning electron microscope uses scanning coils, which creates a magnetic field using fluctuating voltage to manipulate the electron beam. The scanning coils are able to move the beam precisely back and forth over a defined section of an object. If a researcher wants to increase the magnification of an image, either he or she simply sets the electron beams to scan a smaller area of the sample. So once he scans the smaller area, he can easily detect the images in a clear way. So let's see where we are using these scanning electron microscopes. So scanning electron microscopes are most widely used in metal characterization and morphological and compositional information. Like if you prepare composite materials, we require these scanning electron microscopes to analyze the material formations as well as to analyze the characterization of the constructed materials. So why we can use this, or why we need to use this in the characterization of solid materials or morphological aspects or in the composition? Because scanning electron microscope can detect and analyze the surface fracture, and it will provide the information in microstructure examine surface which contaminates the variations in the chemical compositions can be easily analyzed, and also it provides qualitative chemical analysis as well as we can able to identify the crystalline structure of a constructed material. And here it's also used to examine the microchips of your computers, and also it can be used in the essential research tool in the field of life science, biological aspects, as well as in metallurgical studies, as I said, medical fields, and forensic reports. Or in case of forensic science, we can use these scanning electron microscopes. Yes, there are some advantages in case of scanning electron microscope. Yes, as I said, when compared to optical microscopy, we can able to magnify to a higher resolutions and we can get the clear images. This is the first advantage when compared to the previous equipment or previous instrument. And next one is it is easy to operate with a proper training and advanced computer technological associate software to make the operation for as a user friendly. Please try to understand optical microscopy. If you have some semi-skilled operator, that's more than enough. Whereas here we require a proper trained person to operate these scanning electron microscopes. So then only we'll get the clear image, and process is faster, and EDAX analysis can be done within 5 minutes, and generation of data we will get in the form of digital or in the digital form, and the minimum requirement or minimum preparation is required to get the or to complete the process. So these are some advantages, and other advantages we can easily analyze the powder morphology, that is in we studied in powder metallurgy. So it's very easy to analyze the powder morphology, that is particle size, and we can able to analyze the particle size by using a scanning electron microscope, and examination of surface morphology can be done by using scanning electron microscope. Yes, and we have some disadvantages in case of scanning electron microscopy also, that is scanning electron microscopies are little expensive. The cost of scanning electron microscopy will be nearly a crore, like 30 lakhs, 40 lakhs. That depends on the various machines. The cost will be higher, and the size of the scanning electron microscopy is large, and we require a separate area, and the particular area should be free from all the possibilities like electric field, magnetic field, and vibration interference. And next disadvantage is, as I told in the advantage case, we require special training for the operator. Then only we can get the clear image or magnified images, or else it is very difficult to get the images, and maintenance is high compared to other type of machines like which we can consider the optical microscopy or some other devices. The maintenance cost is high in case of scanning electron microscopes, and it involves keeping a steady voltage current through the electromagnetic coils and circulation of cool water. So risk of radiation exposure associated with the electrons that scatter from the surface or from the material surface. And next, it is disadvantage of using this scanning electron microscopy is scanning electron microscopy operators and researchers are usually advised in most of the institutes to observe the safety precaution, that is exposure to the X-rays. High radiations, X-rays are high radiations, very required safety measures. And here only the knowledgeable and experienced researcher being able to identify the actual data which we can get through scanning electron microscope, as well as by using a proper operator can only be detect or identify the proper or actual data. Without having a proper knowledge, it is very difficult to analyze the data which we obtained through scanning electron microscope. That is the main drawback in case of scanning electron microscope. Next type is transmission electron microscopy. So transmission electron microscopy is a technique in which a beam of electron is transmitted through ultra thin specimen. So transmission electron microscopy is based on transmitted electrons. It's very here we are using a very high resolutions. In the year 1986, Raska, a scientist, was awarded the Nobel Prize in Physics for the development of transmission electron microscopy. So let us see the principle of operation of this transmission electron microscopy. In short form, we'll say it's a TEM or TEM. We'll say it's a TEM. So TEM uses high energy electrons up to 300 kilowatts. So accelerating this voltage, which are accelerated to nearly the speed of light. The electron beam behaves like a wavefront with a wavelength about a millionth times shorter than light waves. When an electron beam passes through a thin section specimen of a material electrons which are scattered, a sophisticated system of electromagnetic lenses focuses the scattered electrons into an image of a diffraction pattern. So, or also a nano analytical spectrum. We can see here nano analytical spectrum we can able to analyze by using this TEM or transmission electron microscopy. Transmission electron microscopy. So how we will get the image in this transmission electron microscopy? You can see the arrangements are almost similar to your scanning electron microscope, but here the resolution is higher. So you can see the image. So image which provides a high magnified view of micro and nanostructure, and it displays the accurate information about local crystal structure and which represent the elements which are present in a tiny volume of a metal. And here we are using de Broglie equation, that is lambda E equals to h by 2 m naught E into 1 plus E by 2 m naught c square, where h is the Planck's constant, m naught is the rest mass of electron, c is the speed of light. So here, as we can see, first in the top side, again it consists of electron gun and anode, condenser lenses, specimen, object use, aperture lenses, that is intermediate lenses, then projector lens, fluorescent screen. So this is how the arrangement of TEM. So the tungsten electron working principle. So tungsten filament generates here, the tungsten filament generates a beam of electrons that is then focused on the specimen by the condenser, and the magnetic lenses are used to focus the beam. The column containing the lenses and the specimen must undergo high vacuum to obtain a clear image because electrons are deflected by collisions with the air molecules. Magnetic lenses form the enlarged visible image of the specimen on a fluorescent screen. The photographic film can also be moved aside and the image captured on the photographic film as a permanent record. Here, the electron beams bombardment has been takes place and the lenses focus it on to the specimen will be focused, and electrons are used for imaging constructive purpose, and the images is constructed by transmission or transmitted electrons. The thicker region will occlude more beam of light. So there are some advantages in this TEM when compared to your SCM, or also known as scanning electron microscopes. It offers more powerful magnifications, potentially over a 1 millionth time more than an actual image, provide information on elemental and compounds stresses and also used to get the images which are having high quality in and detailed analysis. It provides the information about morphological structures, crystallinity, and particle size distribution and elemental compositions of the sample. Yes, again we have some disadvantages in TEM. That is, TEM means transmission electron microscopes are very large and very expensive in, and the laborious sample preparation. Yes, it's a sample preparation is very complex. It's a laborious aspect, and operation and analysis is required a special training as of scanning electron microscopes. So samples are limited to those that are electron transparent, and TEM requires special housing and maintenance as of SCM. So these are the some disadvantages we have under transmission electron microscopes. So applications, transmission electron microscopes are used in the field of life science, medical field, biological fields, metal research, as well as forensic analysis. So TEM provides topological, morphological, and compositional and crystalline information to study of crystal metals and to identify the flaws, fracture, and damages, and to view the samples on a molecular level. The semiconductor analysis is analysis and production of manufacturing of a computer and silicon chips. So how we need to provide, as I told, sample preparation is a laborious process. Is how we are going to prepare the samples for TEM analysis or transmission electron microscope analysis. First, we need to fix with a chemical product. That is, we need to go rinse and stain with the chemical products, and we should treat the composites with heavy metal compounds, and we go for dehydration, that is dehydrated with organic solvent like acetone and ethanol, then embedding in resin, that is material is gradually infiltrated with the still unpolymerized resin. Then we require trimming of a resin block and ultra thin sectioning and collection of section on grid. So then the sample size should be less than should be less than or equal to 50 nanometers. The detailed image should be 1 nanometer size, can be analyzed and sometimes analyzed in TM. Next instrument we are looking at is X-ray diffraction. So X-ray diffraction is a rapid analytical technique primarily used for phase identification of a crystalline material and can be provide information on unit cell dimensions. The analyzed material is finely ground, homogenized, and average bulk compositions is determined. So diffraction X-ray diffraction is a used to analyze the crystalline substances like minerals or consists of a parallel rows of atoms separated by a unique distance. Diffraction occurs when radiation enters a crystalline structures and it is scattered. The direction and intensity of a diffraction depends on the orientation of a material. So, how is the working principle of this X-ray diffraction? Here, the X-ray diffraction is a tool used for identifying the atomic and molecular structure of a crystal in which the crystalline atoms causes a beam of incident X-rays to diffract into many specified directions. By measuring the angles and intensities of these diffracted beams, a crystallographer can produce a three-dimensional picture of the density of electrons within the crystal. From this electron density, the mean position of the atom in the crystal can be determined as well as the chemical bonds along with their disorders, and their information can be achieved easily. X-ray are electromagnetic radiations wavelengths and the range of these is 1.1 to 100 angstroms. The principle of operation of this X-ray diffraction is in every atom the electrons are in layers or shells like KLMN shells. We have studied in our high school KLMN, and we have discussed about uh, various electrons, charges, etc. in high school, that is periodic tables, etc. under chemistry, physical chemistry. So here in X-ray diffraction analysis, when the atom is bombarded with an electron, eject one of the electrons from the inner shell. The electrons migrate from the outer shell to the inner shell to fill the gap with a high energy. The quantum of radiation is emitted corresponding to this transmission time scale is approximately about 10 to the power of minus 12 to 10 to the power of minus 14, minus 4, minus 12 to minus 4. The emitted radiation is called X-rays. The production of X-rays are obtained in three ways: by bombardment of metal targets with a beam of high energy electrons, or by exposure of a substance to a primary beam of X-ray in order to generate the secondary beam of X-ray fluorescence, or by using a radioactive source which decays the process results in X-ray emission. X-ray are produced whenever high-speed electrons collide with the metal targets. So, instrumentation, how we are using this X-ray instrumentation. It consists of X-ray tube. It consists of X-ray tube. A high-velocity electron beam on the metal is targeted and X-rays are produced. And next to that, we can see the collimator. So a closed metal plate, which is you can observe in the diagram, a closed metal plate separated between the gap which is used to produce the narrow beam. And we can see a monochromator which is used to observe the undesirable radiations and which allows the required wavelengths to the operator. And here we are using filter, that is zirconium, and crystals we are using chloride and lithium. And the next one, that is here we mentioned in the sketch, we mentioned as crystals. Next we have detectors. Here photographic methods or counter methods we are using. So next one is a goniometer. So instrument, this is the instrument which used to maintain the angle of rotation of when the X-rays are generated by a cathode rays tube filtered to produce the monochromatic radiations. They collimated, and it's been collimated to concentrate and directed towards the sample. The interaction of these incident rays with the sample produces constructive interference when conditions satisfies Bragg's law. Here we are using Bragg's law while we are studying these X-ray diffractions. So Bragg's law gives the angle for coherence. According to as per Bragg's law, we know that Bragg's law tells about angle of coherent and incoherent scattering from crystal lattice. So scattering neutrons waves from the nuclei or by a coherent spin interaction with an unpaired electrons. These re-emitted wave fields interfere with each other, either constructively or disconstructively. That is, overlapping waves either add up together or to produce stronger peaks or separated from each other to some degree, producing a diffraction pattern on a detector. The resulting wave interference pattern is the basis of diffraction analysis. This analysis is called Bragg's diffraction. So it describes the condition of, that is theta. You can observe here in the sketch theta for constructive images to be at the strongest. That is that we are using the equation, that is 2D sine theta is equals to n lambda. N lambda. So where n is a positive integer, lambda is the wavelength of the incident wave, d is the lattice spacing, theta is the diffraction maximum. And let's see the working principle or working operation or working principle of this X-ray diffraction. So X-rays are generated in a cathode ray tube by heating a filament to produce electrons, accelerating the electrons towards the target by applying a voltage and bombarding the target material with electrons. When electrons have sufficient energy to dislodge inertial electrons of the target material characteristics, X-ray spectra are produced. These spectra consist of several components. The most common being is K alpha and K beta. Copper is the most common target material for single crystal diffraction with copper K alpha radiations. The radiation is equals to 1.45418 angstrom. These X-rays are collimated and directed onto a sample. As the sample and detectors are rotated, the intensity of the reflected X-rays is recorded. When the geometry of the incident X-rays impinging the sample and detectors are rotated in the reflected X-ray, the X-ray will be recorded. So when the geometry of the incident X-ray impinging the sample satisfies this Bragg's equation, the constructive images or interference occurs and a peak in the intensity occurs. A detector records and processes the X-ray signals, and it converts the signals to count rate, which is then output to or then we consider it as a output of a device such as print by using printers or computer monitor can get it. And the geometry of X-ray diffraction is such that the sample rotates in the collimated X-ray beam at an angle at a given angle, while the X-ray detector is mounted to an arm to collect the diffracted X-ray and rotates an angle to theta. The instrument used to maintain the angle and rotate the sample is termed as goniometer. For typical powder patterns, data is collected at 2 theta. You can see the angle 2 theta from 5 degrees to 70-degree angle that are present in X-ray scans. So where we are using this X-ray diffraction in the identification or quantification of crystalline phase, measurement of average crystalline size, or strain or microstrain effects in bulk and thin film samples, and quantification of preferred orientation in the thin films. Also, we are using to determine the ratio of crystalline to amorphous material in bulk materials and thin film. And also in characterization of crystalline identification of fine grained minerals such as clays and mixed layers, clays that are difficult to determine optically, and determination of unit cell dimension measurements of a sample purity. So uses or the advantages of this X-ray diffraction is phase identification for a larger variations of a bulk and thin samples can be identified or determined. And the next case is determine of modal amount of a minerals, that is quantity analysis, and determining the thickness and roughness density of a film using glancing incidence, X-ray, reflective or reflectivity measurements. Measuring residual stresses in bulk material and ceramics. Analyzing films such as which is having a thickness as 50 angstroms for textures and phase behaviors. And also it is used to determine the crystalline minority phase, and also to determining of percentage of metal in crystalline forms amorphous layers, which is forms anamorphous layers. So what are the other strengths of using this X-ray diffraction? So other strengths are powerful and rapid, that is techniques for identification of an unknown material. In most cases, it provides an ambiguous mineral determinations, and minimal sample preparation is required, and data interpretation is relatively straightforward. So these are the some strengths of these X-ray diffractions. And again, the same way we have some limitations in the X-ray diffraction. That is, peak overlay may occur and worsen for high angle reflections, and no depth profile information in X-ray diffraction. For mixed material, detection limit is not identified or not specified. For unit cell determinations, indexing patterns for non-isometric crystalline systems is complicated. So next instrument is scanning probe microscopy. So what are scanning probe microscopy? So scanning probe microscope are a family of tools used to make images of a nanoscale surfaces and structures, including atoms. They use physical probe to scan back and forth over the surface of a sample. During this scanning process, a computer gathers data that are used to generate an image of the surface. In addition to visualizing nanoscale structures, some kind of scanning probe microscopes can be used to manipulate individual atoms and move them to make specific patterns. Scanning probe microscopies are different from optical microscopes because the user doesn't see the surface directly. Instead, the tool feels the surface and creates an image to represent it. How they work. So, scanning probe microscopes are very powerful family of microscopes, sometimes with a resolution of less than a nanometer. A nanometer is a billionth of meter, we know, that can be analyzed by using scanning probe microscopes. And scanning probe microscope has a probe chip mounted on the, you can see it's having a probe tip in the image, you can see, which is mounted on the end of a cantilever. The tip can be sharp as a single atom. It can be moved precisely and accurately back and forth across the surface, even atom by atom. When the tip is near to the sample surface, the cantilever is deflected by a force. So, scanning probe microscopes can be measured deflections caused by many kinds of forces, including mechanical contact, electrostatic forces, magnetic forces, chemical bonding, van der Waals forces, and capillary forces. The distance of deflection is measured by a laser that is reflected off the top of the cantilever and into an array of photodiode that is similar to the devices used in digital cameras. So, scanning probe microscopes can detect differences in height that are a fraction of a nanometer above the diameter of a single atom. The tip is moved across the sample many times. This is why these are called scanning microscopes. A computer combines the data to create an image. The images are inherently colorless because they are measuring properties other than the reflection of light. However, the images are often colorized with different colors representing the different properties. For example, height along the surface. So usually the scientist uses this scanning probe microscopies or microscopes in a number of different ways. That is depending on the information they are trying to gather from a sample. The two primary modes of contact modes are, first one is contact mode and next one is a tapping mode. Under contact mode, the force between the tip and the surface is kept constant. This allows a scientist to quickly image a surface. In the next type, that is in the under tapping mode, the cantilever oscillates intermittently, touching the surfaces. Tapping mode is especially useful when the scientist is imaging a soft surface. So there are several types of scanning probe microscopes, and the atomic force microscopes, which we'll discuss in the later part, measures the electrostatic forces between the cantilever tip sorry magnetic force microscopes and measures the magnetic forces, and scanning tunnel microscopes measures the electrical current flow between the cantilever tip and the samples. So next type of analysis is known as atomic, or next type of instrument we can see is atomic force detector. atomic force microscopy, or also known as scanning force. So, scanning force microscopy. Atomic force microscope is designed to measure local properties such as height fraction, magnetism with a probe to acquire an image. The scanning where the scanning probe microscope will not scan the probe over a small area or can over a small area of the sample, measuring the local property simultaneously. The principle of operation of atomic force microscopy is an atomic force microscopy uses a cantilever beam with a sharp tip scan. You can see a sharp tip which sharp tip scan over a sample surfaces. As the tip approaches the surface, the close range attractive forces between the surface and the tip causes the cantilever to detect towards the surface. However, as the cantilever is brought even closer to the surface such that the tip makes contact with it, increasingly repulsive forces takes place over and causes the cantilever to deflect away from the surface. So, the working principle of how it works. So, AFM or atomic force microscopes consists of a cantilever beam with a sharp tip, that is sharp tip probe at its end, that is used to scan specimen surface. The cantilever is typically silicon or silicon nitride with a tip radius curvature on the or nanometers on the size of nanometer. When the tip is brought into proximity of a sample surface, forces between the tip and the sample lead to the deflection of a cantilever forces that are measured in atomic force microscopy, which includes mechanical contact force as well as van der Waals force and capillary forces as well as electrostatic forces. And how we can get the images or also known as imaging modes. So here we have three types. One is contact mode, non-contact mode, and last one is tapping mode. Contact mode, the tip is what in the contact mode, the tip is in intimate contact with the surface and scans across the surfaces. Whereas non-contact mode means the distance between the tip and the surface is continually adjusted so as to maintain the constant deflection. Next one is tapping mode. A stiff cantilever is brought within close proximity of the surface during the oscillations. Part of the tip is intermittently touches or taps the surfaces. So here in the sketch you can see the detector and the feedback electrons, and photodiode you can see the sample surface, you can see the tip as well as laser beam. So some advantages of this atomic force microscopies are it provides a three-dimensional surface profile and sample doesn't require any coatings, and it does not need a high vacuum chamber, and metals can also be analyzed in different environments such as in liquid, under vacuum, or at a low temperature. It provides a very high resolutions. In this atomic force microscopy can be combined with a variety of optical microscopy techniques, and also it can work in the liquid environment. This makes it possible to study biological macromolecules and living organisms. Again, we have some disadvantages in atomic force microscopy, that is scanning area is very small, that is 150 into 150 micrometers. Scanning speed is very slow, and image distortions and thermal drift will be takes place usually, and images can also affect by nonlinearity hysteresis and creep. And this atomic force microscopes probes cannot normally measure in steep walls or overhangs. Cantilevers are more expensive, which we are using in these applications. And or let's see the applications where we are using this atomic force microscopy. In the nanotechnological analysis, biological research, we are using this atomic force microscopy. Next instrument is electron probe micro analyzer, that is also known as EPMA, electron probe micro analyzer. So electron probe micro analyzer is a micro beam instrument used primarily for thin situ or thin sheet of non-destructive chemical analysis of minute solid samples. This electron probe microscopy analysis is also informally called electron microprobe, or just say it's a probe. It is fundamentally the same as scanning electron microscope with added capability of chemical analysis, whereas in case of scanning electron microscope we are not conducting any chemical analysis, whereas here we is to conduct chemical analysis. In the image you can see there is a primary electron source and backscattered electrons, cathode cathodium screens, secondary electrons, X-rays, absorbed electrons, induced voltage, electrons that passes through the specimen. So here, based on this sketch, you can easily understand the working principles or the various components. An electron microscope operates under the principle of, that is, of solid materials, is bombarded by an accelerated and focused electron beam. The incident electron beam has sufficient energy to liberate both matter and energy from the sample. These electron samples interactions mainly liberate heat, but they also yield both derivative electrons and X-rays. These quantized X-rays are characteristics of the element, and this electron probe microanalyzer analysis is considered to be a non-destructive. So it is possible to reanalyze the same material for more than one time. This is the specialty of this electron probe microanalyzer, whereas in other cases we cannot able to go for reanalysis. We need to prepare the next or new sample, then only we can able to go with the analysis process. So where all we are using this electron probe microanalyzer? In the quantitative electron probe microanalyzer analysis is the most commonly used method for chemical analysis of geological materials at a small scale. In geological applications, we are using this electron probe microscopic analyzer. And electron probe microscopic analyzer is also used widely for the analysis of synthetic metals such as optical wafers, thin films, microcircuits, semiconductors, and superconducting ceramics. And some advantages and disadvantages, also known as strengths and limitations of electron probe microscopes. So some advantages we have is yes, in every instrument we have some advantages and disadvantages. You can take any man-made things, like if you consider we are being a mechanical engineer, we are very fond of cars. In any cars we can find some advantages and some disadvantages, like in uh, in safety wise some cars are good, in fuel efficient wise some cars are good, whereas they failed with respect to safety aspects where where we have high safety, there we won't get the expected fuel efficiency. So in the same way, here also we have some advantages and disadvantages. So what are the advantages and disadvantages of this electron microscope or electron probe microscope is, or electron probe micro analyzer is, an electron probe micro analyzer is the primary tool for chemical analysis of a solid material at a small spatial scales, and it spots the chemical analysis which can be obtained in situ, which allows the users to detect even a small compositional variations within textural context or with chemically zoned materials. So these are some advantages of this electron probe microanalyzer, and some disadvantages we have under electron probe microanalyzer. That is, electron probe microanalyzer cannot unable to detect the lightest element like helium, lithium, etc. And probe analysis or electron probe analyzer analysis also cannot distinguish between the different valence states of iron. So these are some disadvantages we have under this electron probe micro analyzer. So these are some references I used to prepare this present presentation. Thank you for your patience listening. Thank you all. And if you have any doubts, please contact me through my WhatsApp and you can try to solve your doubts. Thank you very much. Thank you all.